let's talk about the design benefits of test-driven development. We talked about the benefits that regression gets out of test-driven development. It keeps an eye on the code, and when things begin to fall apart, it immediately tells us and gives a rapid feedback. But how could it possibly influence the design of an application? Don't we just design and then don't we just code? Where does test play any role into this? Well, it turns out that it's really hard to take an arbitrary code and start testing it. In fact, a well-designed code is easier to test. A well-designed code will require fewer tests as well. A well-designed code will fail less, so it can be easily tested as well. So there are some benefits to writing tests to influence the design of the code. Imagine I give you a function which is 10,000 lines long. Well, that's no surprise. A lot of code in the industry is 10,000 lines or more. Now, if the length of the code is so long, the number of permutation and combination we have to take through the code is just enormous. There is no real possibility of writing any reasonable number of test cases to cover all the different combinations in this code. So that code pretty much is really untestable. Why? Because it's been poorly designed. We know that long methods are really poor design, reflection of poor design. Now, long methods are hard to maintain, hard to understand, hard to debug. The list keeps going on, and there are so many design flaws in long methods. If we start out to write test cases on a method, we will quickly realize that beyond a certain level, we cannot grow this method. We have to modularize it and create other smaller methods and write tests on them. So fundamentally, writing test cases forces the code to become more modular. Likewise, if a code has a lot of dependencies, it becomes really hard to write tests on it because a test becomes brittle because of these dependencies. As a result, we tend to decouple the code as well. So as the first start, a test that is, the code that is written through tests ends up being more cohesive, narrow, small, focused, has a single responsibility, and also has less coupling. So high cohesion and low coupling is one example of a good design code, and test influences that quite a bit. So in other words, as Ken Peck nicely put it, he said, test or unit testing he was focusing on mostly. So unit testing, he said, is an act of design more than an act of verification. Now, no doubt about it, right? We definitely get the verification benefit from these test cases. We cannot argue about it. But we talked about how the regression helps us also. So there is a benefit from unit test for verification. But unit testing is relatively more, an act of design than an act of verification. So a good tested code is a good design code in general. But that's not a guarantee though. We could write bad code, we all have done. Likewise, we could also write bad tests. So if the test is poor, it's not going to influence a better design. So a good written test can influence a good design. So we have to keep an eye on the quality of tests to get a better quality of design as well. So a way to design software is using these test cases to influence the design of the code. What are the different types of tests that we write? Here we focus mostly on unit tests, but there is also black box testing and white box testing, functional testing, integration testing, acceptance testing, and then of course unit testing. Within the realm of unit testing though, we can look at three types of tests: positive, negative, and exception tests. A positive test is to simply say the code is doing what it's supposed to do. I put money into my mortgage account, my mortgage value should go down when I deposit money into my mortgage account. So I'm paying off a little bit of my mortgage, so the amount should go less. That's a positive test. A negative test. What if I put money into a mortgage account that's closed? You may wonder, really? Is that necessary? Well, yours truly went through that same problem. I closed a mortgage account with a bank. I decided to refinance it with another company. Well, a couple of months went by and we noticed that money was missing from my account. And so we started looking through it and eventually found out that the mortgage we closed was still taking money from my bank account through the automated deposit. Well, somebody who wrote the code forgot to really say, well, gee, this particular account is closed, the mortgage is paid off, transferred over to another organization. We shouldn't be putting money into this anymore. That's an example of a negative test. When the preconditions are not being met, or when the surrounding situations are not what you expect, when the state of the object is not in a valid state to receive that particular call, what do? Those are negative tests. Exception tests are to make sure the code is throwing the right kind of exceptions. We often expect the code to throw some exception, but is the code really throwing that exception? If you looked at the video for the regression benefit of TTD, we wrote an exception test in there. It keeps a guard to make sure the code is actually throwing the right kind of exceptions. If we modify the code tomorrow and the code is no longer throwing that exception, we want to know about it rather quickly. That feedback loop again. So when you write tests, write three kinds of tests: positive, negative, and exception tests. But there's also one more type of test you could write, which is called a performance test. How often do you work in jobs where we are told that performance is very, very important? We're told that a particular request on a website, for example, should take no longer than 200 milliseconds, or a particular data crunching shouldn't take more than 50 milliseconds, or whatever that could be. But all these claims about performance go a waste and come back to haunt us if we don't have a way to get a quick feedback when it falls apart. Imagine you spend 2 full days and a lot of intensive refactoring to get performance really under a certain level. Well, you test this a few times and the performance looks really good. Awesome. Let's say a few months goes by, we put features, we add more functionality, we refactor the code, but nobody really checked back on the performance rigorously. So a few months later, we find out that suddenly, when we try to run this particular example, well, the code is not performing. It is no longer taking that 50 milliseconds. It's taking 2 seconds to run. Oh my gosh, what do we do now? Well, all that code change that's happened over the several months, we have to deal with it all of a sudden. But instead, when somebody tells you performance is important, ask them to write a test for it. If your tester says this code has to perform within 200 milliseconds, or your business analyst says this code has to have a response of less than 1 second, ask them, please don't tell this to us, write a test for it. They could write an acceptance test, which can then get translated into low-level unit test at various different levels of the code. And you can set up an environment with a certain test data, with a certain configuration, and say, always make sure this code runs faster than this given particular time. There are tools, in fact, to help us with this. One such tool is called JUnit-Perf, for example. JUnit-Perf, for example, is a JUnit extension, and JUnit-Perf will give us time testing. It will make sure that a piece of code not only passes a particular expectation, but it completes within a certain duration of time as well. So having performance test is as important as any other types of tests. But let's focus on unit tests. So what's a unit test? Well, I'll give you a good answer for what a unit test is. A unit test is a test on a unit of code. That was simple, wasn't it? Well, that was pretty lame as well. Okay, a unit test is a test on a unit of code. That brings up the question, what's a unit of code? And therein is the most important thing we should keep in mind. A unit of code is a smallest piece of code that does useful work. Now, let's start with this definition and work from it. A unit of code is unit tested. A unit of code is the smallest piece of code that does useful work. We can think of a smallest piece of code, getters and setters. Getters and setters are the smallest piece of useless code. What does a getter typically do? Returns the field. What does a setter typically do? Sets the field. Of course, sometimes we may put certain operations in the getters. Sometimes we may put a little test in the setter to verify that the value is valid. But 90% of the time, the getters and setters are pretty darn useless. Don't write unit tests for getters and setters. Getters and setters should come into picture while we are writing other tests and other functions, And so there's no reason to spend time writing tests on these kind of setters and getters. In fact, when you start writing unit tests, try to focus on testing behavior rather than state. If you ask me one fundamental thing I've learned over the past several years, that is to focus on behavior rather than state. If you start testing the state, you end up creating objects that are heavy on state. If you start testing the behavior, you move quickly towards the purpose of the application rather than polluting the objects with states. So focus on writing test for behavior. Now, when you start writing these tests, you wouldn't focus on writing tests for getters and setters, great, but then there are other methods that are doing some useful work. What if there's a method that has a loop, a recursion, very complex logic in it? That's definitely a useful code, more than likely, but that's not a smallest piece of code anymore. So a unit is a smallest piece of code that does useful work. You must be able to break this code into a smaller piece where it does useful work, and breaking it any smaller wouldn't make any sense, and making it any bigger would not keep it small, obviously, because it would have some intricate logic, loops maybe, recursions or iterations and stuff like that. So the point really is a unit test is on a unit of code where a unit of code is the smallest piece of code that does useful work. A unit is not a class. A unit is often a method, a small function, if you will. But how do we typically write classes? We typically write class by opening a file, thinking about what this class should do. We start creating fields, some methods around it, and we just grow this class with whatever comes to our mind. Then we throw it across the fence and say, here is the class I wrote, use it. Oh, by the way, good luck. Well, the point is, we don't want to create a class with implementation in mind. Instead, start with the tests. How does TTD change this? You first put yourselves in the shoes of the person that's going to use your code even before you write the code. So you start thinking about how would somebody use this? What kind of method would they call? How would they want to initialize this object? What kind of parameters they want to pass? What should be the type be? Hey, does this feel lightweight or does this look verbose and heavy? Is this really a burden on the user? So when you're designing your code, you think through these from the user's point of view and then come to write the code. But here's another thing to think about it. You would start writing some test cases where the first few test cases are going to appear rather trivial, and you're going to return fake result from these methods. The reason we do this is we want the first few tests to grow the skin of the interface of the object or the methods, and then we want the later test to really form the guts of these methods. So the point really is the first few tests are slowly forming the interface or the skin, and as we write more tests, slowly the internals of this function begins to grow. Well, why would we want to do this way? Remember how we read about object-oriented programming. We learned that interfaces are very important, and once we have a really good interface, we can vary the implementation. Well, if that's really true, then why in the world are we so eager to start with the implementation rather than trying to grow the interface? So let the first few tests help us to build the interface of the functions, and then the later tests let it really provide the implementation of these functions to grow to fill that gap and provide the support for this function. So let the first few tests help you to think about the usage of this function, and the later tests help us to define the internal structure of these functions. We can write unit tests, but often people write tests after they write the code. Oftentimes it becomes really hard. The longer we have gone without writing the test, the harder it is to write meaningful and effective tests. But what if we write the test first, even before we write the code? So in test first coding, we write the test, often a failing test, and then come back to write the test code, enough code to make this test to pass. So in test first coding, we write the test first, and then minimum code, just the bare minimum. Sometimes we fake the results and give the response so the test would pass. And by doing this, we are really helping to structure the code, form the skin, and then the guts of the function that we are trying to model, the one we're trying to design. So what are some of the benefits of this? Well, when it comes to this, it completely reverts the way we think of the code. Rather than rushing eagerly to create the implementation, we grow the skin, the interface, and then once we got something nice and usable and practical, then we put minimum details in it. It helps to keep things minimum and practical from that point of view. The code becomes robust. This is the regression benefit we get out of it. So as we are writing the test and writing the code, anytime we make a small change to the code, immediately these tests wake up and verify. And if anything were to deviate from the expectations, they immediately tell us. So as a result, the code is a lot robust, and we can release with confidence that the code that worked yesterday works now with the change we just made. It is a good way to verify that everything that worked again works, and that really helps to make sure that the code is still functioning. From the point of view of robustness, there is one more feature also. While verification and robustness may kind of hinge on each other, regression is really verification. But robustness is something a little bit more than that as well. Now, when I'm trying to write test cases, I often start with the test and say, what kind of test I want to write on this code? And oftentimes I'm quite pleasantly surprised how many tests I identify about various different conditions I need to take care of. For example, let's say I'm interested in modeling insurance policy. And as I start thinking about it, I immediately ask myself, what if the policy expires today? What if it expires tomorrow? What if it expired yesterday? What if I'm in a time zone and it expired a few hours ago in another time zone? What if the particular date of expiration is set in a reverse order as an input coming in? What if this insurance policy belongs to a group of policies and the duration exceeds the limit provided by that? So as I'm sitting down to write these test cases, I think of all these various edge cases I need to worry about, and very systematically I write a test to verify those. As a result, the code is very robust because it takes care of various different scenarios that I need to worry about. And very quickly, it becomes very fulfilling that you are able to make sure the code is there to handle various edge cases and various values that could become problematic in your code. And those really come to strengthen your code. And when different kinds of data come in, the code says, yep, I'm handling that because the test cases are there to tell me to take care of that. So that is where the robustness of the code comes in. It gives us the confidence as programmers. We can walk with our head up saying, yep, the code I wrote actually works. I can release this with more confidence. In my own personal experience, when I've started doing test-driven development, I release more often with great confidence than being fearful when things are going to fall apart and break. It gives us the ability to decouple the code from its surroundings. It's very difficult to start testing code which has a lot of intricate coupling dependencies. So we normally do dependency inversions and we decouple the code. We also sometimes eliminate dependencies just because it becomes hard to test the code with all those dependencies. So overall, that contributes to better design of the code as well. And it also serves as a form of documentation. Whenever I start learning a new library or even a language, I often get the test as a way to of documentation. For example, I started writing the book on Java 8 way before the Java 8 was released, nearly about a year and a half before. So when I started writing the Java 8 book, there was no Java doc available for Java 8. I can't complain. I can't sit there and say, well, there's no Java doc for me to understand. Well, my friends were the unit test. So I downloaded the source code for Java, and the first thing I look for is those unit tests. And looking at the unit test, I can see, oh, that's the expectation on this code. This is what this code is doing. And whenever I was in doubt, I would go through the unit test that these Oracle developers have written for Java 8, and I can see how the code actually behaves. It also tells me a nice story of how the code could be used in a certain context. So unit tests are a great form of documentation. Automated tests are a great form of documentation. So we can use these pretty much to create our test cases, and this in turn greatly influences our design. It helps us to create clean code that works. Ron Jeffries said that when you try to write test cases, you end up writing code. It influences you to write code, clean code that actually works. You're not interested in creating clutters and complexities. You are interested in just getting minimum code to work, and the code ends up being clean provided we pay attention to the test we write and the code we write. The code becomes very predictable. We don't have mounting errors in the code. We make a change and immediate feedback loop tells us, oh, wait a minute, this code doesn't work. Or when we're trying to make a design enhancement. The time I was really not sure about automated testing and the day I was convinced, I very clearly remember. I made a design change. I thought through it about a few times. I made the change to the code and the compiler said everything is good. Then I ran my unit tests and several of my tests failed. To my surprise, that the change I made had violated some expectation in different parts of the code. The ability to get that quick feedback cycle gives us the ability to modify the design and move on without mounting errors and worry and fear that I don't want to change the design because I'm afraid that something will fall apart. What if you can quickly make a change to the design and get that feedback loop to tell us everything is still okay? That is invaluable. It helps us to program with intention. We can program with intention to say, well, this is what I want the code to do, and very systematically we can write minimum code to serve those purposes. We're not sitting around and saying, yeah, while I'm here, let me handle these other 7 things too. No, I have a test that I want to pass. If there are other things I need to do, I'm going to write a test and then come intentionally implement code for that. So that's again a part of discipline we have to develop. It doesn't come automatically. It helps us to create code that's simple and also minimum. You don't want to be writing a lot of code because you have to write tests for those. And of course, I would rather not write tests for code I don't need to write. It forces us to keep things minimal. And of course, we try to strive for simple design and simple code, which is easy to understand, easy to maintain. These are influences of TTD, but we have to have the discipline and put effort to achieve these as well. So this can give us quite a number of benefits to developing code that is easier to test, easier to work with. So fundamentally, when it comes to test-driven development, when it comes to unit testing is an act of design, then an act of verification. It gives us the ability to look through the code from the point of view of the user of the code, grow the interface, then come and implement the code. And then, of course, it gives us quick feedback cycle when we begin to modify the code. But the question is, how do we approach the design using TTD? Let's take a problem for now, get ourselves familiarized with the problem, and then we will jump into doing TTD of this in the next part of this presentation. So let's start with a little problem to begin with. Well, the problem I have here is we're going to implement the game of tic-tac-toe. We're going to use unit tests to write this code. But let's first of all do a strategic design, come up with an initial design idea, and then we will jump into tactical design in the next video and talk about how we can approach it. So here's my recommendation. Let's go through the problem real quick, but then I'm going to ask you to pause the video and try to do an initial design and then come back and resume the video after that. So let's try this. The problem given is this. The game has 2 players. So there are 2 players who are interested in playing this game, but each of them get 3 pegs each. One of them gets a peg which are all X pegs and the other gets all O pegs. There's a 3x3 grid. So you have a little rectangle with a square with the 3x3 grids on it. The objective of the game is for the players to place the pegs by taking turn, and whichever player first places their pegs in a row or a column or diagonally gets to win. The game keeps track of the winner and also keeps track of the number of times that person has won the game. So that pretty much is the code we are going to work with. My recommendation at this point is that you please pause the video. And once you pause the video, go ahead and try to come up with initial set of classes, a very high level design. And once you are done with it, then come back and resume this video and let's compare notes about what classes you came up with and some of the classes that I'm going to list here, and then we'll be ready to move on. So go ahead and pause now and come back after you've done an initial high level design, 5 minutes max, and then come back and see what you have. All right, so I hope you came back after you tried this design. So let's now talk about a few classes that come to mind. I worked through this problem with a few number of developers around the world, and I have a common set of classes that everybody almost immediately jumps onto. The game has two players. So typically somebody says, oh, you got a game class potentially. It's got two players, so there are player classes. And with three pegs, there's a peg class. And of course, then comes the grid. So we have a grid and potentially a cell in the grid. And of course, the players can take turns to play. Somebody recently said maybe a turn is something we need to have modeled as well. And the first player can place the pegs and they take turn to place. And whoever the first player who places the three pegs in a row or a column or diagonally wins the game. So there is a rule for the game that is supposed to check for these validations. And then of course, there's a store that's going to store the scores. So we have a score. We have a score history that we need to store as well. And then of course, the player information is kept in there. So those could be an initial set of classes that we can identify. You may have come up with more classes or fewer classes. That's perfectly fine. You could potentially put them into a little UML diagram if you want to. For instance, let's start with the player for a minute. So we could say that we have a class called player. Well, that's great. We have a player. We got one out of the way here, the player itself. That's great. In fact, let's actually account for each one of those here. So let's go ahead and say we have a player to begin with. And so we identified the player in the picture. We also have pegs. So let's go ahead and create a class for peg. Now we know that a player can have multiple pegs. So what you could do potentially here is you could draw an association between them and you could say that this is going to be a player has three pegs. Now remember that each player has three pegs, but the peg itself could be of two different types. You could make this a little bit more by saying, oh, you have an X peg and an O peg. So maybe we should have an inheritance hierarchy potentially here. So we could possibly say, here is our X peg and here is our O peg. And then you could, of course, say this is an inheritance hierarchy between the two potentially. So you could decide to go one way or the other depending on what you're trying to do. So I have a peg class obviously here, and now we have an inheritance hierarchy between the two. So we can say X inherits from peg and likewise O inherits from peg. And then of course this is an association we talked about, and this is going to be a value of 3. So that is the diagram we have so far. Then we could say, well, we got the grids obviously, and the grids have cells in them, total of 9 cells if you recollect. So we could say that in this particular case, we have a bunch of grids on our hand. Well, let's go ahead and try something else here. Let's move this a little closer. And we could say that we have a grid. So this could be a grid we can place over here. So there goes the grid. We could also place the cell, for example. And of course, we can say that a grid has cells. So we could use an aggregation for this. And once again, in this case, we could say there are 9 cells available for us in this particular case. So we can see that we have taken care of grid and cell. Well, turn appears to be more of a logic than a class, so we could ignore that. But there's a rule, so potentially there's a rule class that has to apply the rule. So we could say there's a rule class sitting here. Not exactly sure what it relates to, so we could talk about that as well. And then comes along the game. And what is a game compared to a rule? Oh, one thing we forgot in this discussion is the GUI that we should really think about. So there's got to be a graphical user interface as well for this. So we could say here is the GUI. And then of course the game itself, we can put that as a class here, not knowing how that's going to relate to the rest of the stuff. We got to think about that. And then of course, what else is left here? We have the score and the score history. So we could talk about a score store and the score itself. And of course, we could say here is the score. Now the score obviously has to depend on the player. So we could put an association between the score and the player of some sort. And then of course, the score store is going to contain all the scores. So we'll say store. And then the store is going to aggregate all the different scores. So let's go ahead and draw up an aggregation between those two like this. And of course, a score has to be for a particular game. So we may say a score has to be related to a game potentially, and we could bring that in as well. And of course, the GUI potentially has to display all the grids and manage it. So you could argue that a GUI contains a grid, if you will. So you can start putting together a class diagram with all these different information together. That's our strategic design. Now remember, if you can, please go back and review the strategic design video, and we talked about this. A strategic design is a direction, is a suggestion. One of the worst things we can ever do is take a strategic design and say, here you implement this class, here you implement this class, here you implement this class, and then we let people just go soldier and implement this design. But instead, a tactical design should validate and evolve a strategic design. This is a great design idea to begin with, but don't feel compelled to implement each of these classes. Instead, start by elimination and look at one that you want to start with, and then start driving the test of it and design it using these test cases. And that is what we will do in the tactical design. So we will talk about this in the next part, how we are going to continue with this test-driven development. The design benefit of TTD in part 2 will get into the tactical design of things.